Yeah, I gotcha.
Okay. Okay, so question number one, example one, it says use five rectangles of equal width to find an approximate area of the region lying between the graph negative x squared plus 5 and the x-axis between 0 and 2. So we're going to draw a picture and we're going to do RRAM. What's up?
Can you check this to see who's in the waiting room?
Oh, she's in the waiting room?
I don't. Is anyone in the waiting room?
All right. So the first thing I'm going to do is I'm going to graph this from 0 to 2. Now it doesn't touch the x-axis because 2 squared is 4, negative 4 plus 5 is 1. So it's going to look something like, and I'm going to exaggerate, I'm going to make it big. I'm going to say here's 5, and my axis is not to scale. I'm going to say that's 2, and it looks something like that. And that has to be the value of 1. Yeah, and I can see there's a big delay. See here, I have it on this guy too. Oh, look, that's Van of the cream. I don't know if you can see them, but all right. So here we go. Oh, sorry, Abdul Kareem. You had a question?
I got it. No, I was just saying.
Oh, okay. She came on the Zoom. Oh, sorry. Okay. All right, here we go. Don't worry. We'll. Okay. Yeah. Let's draw a picture first using RRAM. Okay. How many rectangles did they want? 5. All right. So let's see if I can fit 5. 1, 2, 3, 4. Okay. And then we're doing RRAM, so it's gonna look like this. Because this is a decreasing function, there's Marchan right there. Hey, Marchan. Because it is a decreasing function, this approximation is going to be an under approximate. That's not a big deal. I want to know the delta x, and I want to know what those x values are that determine the height. So my change in x is nothing more than, here's 0, that's 2, so 2 minus 0, and I'm dividing by 5 rectangles. So my delta x is 2/5 or 0.4. Are we still okay? All right. So all I'm doing, I count 1, 2, 3, 4, 5. All I'm doing is finding the height of each one of those rectangles, and I'm multiplying it by the width. So let's see. The height of my first rectangle is going to be, let's see, the function is negative x squared plus 5. So I'm going to put a negative parenthesis, and it's going to be, that has to be, okay, I guess first let's label the x coordinate. That's a 2/5. And then 2/5 plus 2/5, that's a 4/5. And then 4/5 plus 2/5, that's a 6/5. And then 6/5 plus 2/5, that's a 8/5. And then 8/5 plus a 2/5, that's a 10/5, which is the same thing as 2. Okay. Did everyone see how I got those values? I just kept adding the delta x because that's what they're. Okay, so here's my height. So the height is dictated by this curve, and this curve is y equals negative x squared plus 5. So the height of my first rectangle, let's see, negative, oh, not negative, the negative in the front, 2/5, close it squared, because that's what it says x squared plus 5, close it, and that's your height of the first rectangle. Height of first rectangle. And I got to multiply by the width, which is just 2/5, plus the height of the second rectangle is going to be negative in the front, 4/5, close it squared, plus 5, close it, times 2/5 again. That's the height of the second rectangle. Well, height times width. The 2/5 is the width. And all I'm doing is finding the area of each rectangle, guys. Plus, parenthesis, negative in the front, 6/5, close it squared, plus 5, close it, times 2/5, plus, parenthesis, negative on the front, 8/5, close it squared, plus 5, close it, times 2/5 again. And that's the fourth rectangle. And the fifth rectangle, the height is dictated by that 2 value. Negative in the front, 2 squared plus 5. That's my expression for the height. That will give me the y value times the width. I gotta add all those up. So I'm gonna label, this was my first, second, third, fourth, and fifth. That's the area of each one of those rectangles. Let me get my little calculator out. Did I ever hook you up with a calculator? You just didn't bring it. But you do have it though, right? Okay, better than what Paracello said. Hey Paracello, in case you're watching this video. She doesn't know where she has hers at. She just knows it's somewhere. Let's see. I'm gonna type it in here. Negative x squared plus 5 and alpha trace y1 at 0.4 times 0.4 plus alpha trace y1 at 0.8 times 0.4. You don't have to do it like this. You can just, however, maybe do it the long way and see if we get the same thing. Y1, what is it, 1.2? 0.4, yeah. Times 0.4 again. Now I feel like I should have just not put the 0.4 and just did it at the very end times 0.4, but that's fine. Plus alpha trace 1.6. I'm not being consistent. I should have kept either the fractions or the decimals. And here I am just going back and forth. Those are my fractions, guys. The 1.2, the 1.6, the 0.4, the 0.8. That's the 2/5, the 4/5, the 6/5. Like, we're cool with that, right? And then finally, alpha trace y1 at 2. And I'm multiplying that by 0.4. If I did everything correct, did you guys get 6.48? Okay.
Yes.
Awesome. Area using 5 rectangles is 6.48. Okay. I want to use sigma notation. So I'm going to put a rectangle, a sum, which is just a sigma. It should be straight like that. And then usually you want to use the letter either I, J, or K. It doesn't matter what letter. I guess. Go ahead, ask. Oh, I thought someone had a question. You want to use the letters I, J, or K. It doesn't matter what letter. You can actually even use the letter A, B, C. But I, J, or K is what's used traditionally. And this means how many rectangles you have. So I start with at least one rectangle. So usually you don't want to start at 0. And I have how many? So there it is. So I'm using 5 rectangles. And I could either, let's see, I need to figure out an expression that when I plug in a 1, I'll get a 2/5. When I plug in a 2, I'll get a 4/5. When I plug in a 3, I'll get a 6/5. When I plug in a 4, I get an 8/5. And when I plug in a 5, I get a 2. They're making it simple because all the delta x's are consistent. They're all 2/5 apart. So I know that I can just do this. Negative parenthesis 2/5. And then I can put the letter K, close it, squared, plus 5. There's my width. And it will work, because look, I'm going to slow down because I don't want you guys to be robots. 2/5 times 1, 2/5. 2/5 times 2, because remember, these are integers. 2/5 times 2, well, 2 times 2 is 4, 4/5. 2/5 times 3, well, 2 times 3 is 6, so 6/5. 2/5 times 4, 2 times 4 is 8, 8/5. 2/5 times 5, the 5's cancel out, it's a 2. And then I multiply, that just gets me my height, and I multiply that by the width. There's many ways to display it. It doesn't have to look like this. You'll probably also see it. Like this, and they're the same, guys. So I'm gonna put some notation. These are all the same. You know what? I'm gonna use the letter I. I equals 1 all the way to 5. So this just tells me, I'm gonna circle them for good notes. I'm gonna put how many rectangles? So you always start at 1. You could start at 0. You could, but it just complicates things when your summation, because usually that stands for how many rectangles. But you could start at 0. You can find an equivalent expression that's starting at 0. So here we go. What did I say? We're going to use the letter I and write it differently. So you could write it like this. F of, let's see, that's a 2/5. 2/5 I, close it, times 2/5. And that will give you the same answer. So I know, you're like, Chav, how is that the same thing? Well, let's see. Let's see what this means. This means F of 2/5 times 1 times 2/5 plus F of 2/5 times 2 times 2/5 plus F of 2/5 times 3 times 2/5 plus F of 2/5 times 4 times 2/5 plus F of 2/5 times 5 times 2/5. Child, that's not the same. Yes, it is. This is a function f evaluated at 2/5 at 0.4. This is a function f evaluated at 4/5, so at 0.8. This is the function f evaluated at 6/5, 1.2. This is a function evaluated at 8/5, so 1.6. And then the function evaluated at 2. Does that make sense, guys? Or does that not make sense?
No, that makes sense. Would you have to put in something for F though, or is that?
Well, what is f? F, I guess right there. There it is. I guess I should have probably defined it in here. F of x is negative x squared plus 5.
But like if you were to put this in the calculator, would you
Oh,
plug in F there?
yeah. If I have it in y, you know what? Good thing you told me that. Let's use the sigma notation. Let's see if we see how we got the number 6.48. Let's see if we get the same thing. Math. Let's put it all together. Let's see. Summation number 0. And I'm going to put x here. I'm going to start at 1. And I'm going to end it at 5. And my expression has an x. So all I got to do is call it out. F of 1. Y1. And in here, I'm going to type. Let's see. What am I going to type? I'm going to type 2/5 x. Or I can, or what's the same as 2/5? 0.4? I'll do the 2/5 to stay consistent. So here it is. 2/5, and then I'm going to put the x next to it. X. And I'm going to multiply this. So there it is. I close it, and I'm going to multiply this by 2/5. Now, if I'm fake, this will not be the same number, but I'm just doing this out of a spur just because Estrada told me to. And it should work. So I'm kind of nervous. Let's see. Okay, I'm not nervous anymore. You see how it works. So it's the same. Look, this expression here is the same as the expression I have here. Now, I'm going to warn you guys in advance. It's very easy to become a robot. If you sometimes students get lost, and Romero can tell you she has experience with this. It's very easy to become a robot and be like, I don't know what's going on, but I see the pattern, and I'm just going to do that pattern, and I'm not even going to worry about it. Try really hard to not be a robot. Try really hard to understand the little intricacies. Cool or not cool? Okay, is all this right here so far make sense? Okay. And I forgot, we also got Abdul Karim on Zoom, and Abdul Karim can also tell you that it's very easy to become a robot, but hopefully you understand the little patterns. Okay, we're going to do the same thing, but this time with LRAM. And we're going to see if this complicates things or not. So let's see. I'm going to do the grid again. So let's do that same grid. And we're still working with the same function, negative x squared plus 5. My scale is not perfect, not to scale. Let's see. It's just random, guys. It's not perfect. Obviously, that 2 and that delta x and my delta y look like they're about the same because, my width here, that looks like it's the same as that. So my scale is obviously off. I'm doing that on purpose. Not a big deal. Are we okay? All right, we're doing LRAM. So let's see. That looks like it could be a good location. 2/5. My delta x is still the same. 4/5, 6/5, 8/5, and then finally when you get to 2, that's the same thing as 10/5. All right, and by the way, in case you don't remember, like how do you always get the delta x? It's always going to be whatever you start. We started at 0. Wherever you end, we ended at 2. 2 minus 0 divided by how many rectangles you have. All right, they wanted me to use what LRAM? What does the L stand for? Left. So here we go. I go from the left. I go until I hit 2/5, a horizontal line, and then go straight down. Start at that curve, straight down to 4/5. Because I have a strictly decreasing function, an LRAM for this is going to give me a over approximation. We're going to start it just like we did before. I just want the areas of those rectangles. I have 5 rectangles. And then we'll come up with an expression to see if we can figure it out. So let's see. The first rectangle, width times height. The width is always 2/5. My height, so negative 0 squared plus 5 times 2/5. That's my first rectangle. Plus the second rectangle, 2/5 squared plus 5 times 2/5. Plus 2/5 squared plus 5 times 2/5. Plus, yes. That's 4/5. I did that on purpose. No, that was not on purpose. I had a brain fart. Negative parenthesis 6/5 squared plus 5 times 2/5. And I wasn't able to fit it. Negative 8/5. Oh, there's the last one, right? Squared plus 5 times 2/5. All right, take your calculator and let's see what this is. Let's see. This time I'm going to be smart. And I'm just going to multiply the whole thing at the very end. Because see how, okay, real quick. See how they're the 2/5 on all of them? I can factor it out and just do it at the very end. So I'm going to go y1 of 0 plus alpha trace y1 of 2/5. This time, I know, consistency. One time I'm decimals, next time I'm fractions. Alpha trace y1 of 4/5 plus alpha trace y1 of 6/5. Yeah, if I would have connected it, it could have been faster. Plus alpha trace y1 of 8/5. Hopefully I haven't made any mistakes. Oh, that's the last one right there. And enter. And then I'm going to multiply that by 2/5, so times 0.4. So I got 8.08. Is that what you guys got? Okay. Let's see if we can come up with a sigma notation for this. How many rectangles do I have? 5. So I'm going to say, let's use, what letter have we not used? J. Start at 1 and we end at 5. And let's see, I want to get a 0, and they still all differ. All the x values differ by 2/5. So the hack is not really a super hack. How do I get it to always be by 2/5? So it's going to look very similar to this one. But I need the first term to be a 0. So how do you think we would do that? You guys have an idea?
I have a question.
Yes.
So for the J equals 1, is that like where you start, or is that like what you're going by?
This means that's my start, my first rectangle.
Okay, then can we do?
Go ahead. Abdul Kareem, you there?
Oh, you froze. I was like, I don't know what happened. Okay. I was gonna say, so could you do like J equals to 0?
You can, but look how weird it sounds to say the 0 rectangle is my first. So it's going to complicate things. Does that make sense?
Yeah.
So I would always start it out at j equals 1. What's up?
Can we do 2/5 J minus 2/5?
Yes, you can. But you 2/5 j minus 2/5. Let's make that prettier. So can I factor out a 2/5? And then what would I have? J minus. That's way prettier. J minus 1. And then it's prettier because you want to see integers for like the j minus 1. You know what I mean? And then this is going to determine your height. And then times 2/5. Does it work? Yes. My first rectangle, 1 minus 1 is 0. 0 times 2/5 is 0. 0 squared. My second rectangle, 2 minus 1 is 1. 1 times 2/5 is 2/5. My third rectangle, 3 minus 1 is 2. 2 times 2/5 is 4/5. Do you guys see how it works? Perfect. You had a question, Aslada?
No.
Okay. Yes, Abdul Kareem, you were right. We can start at a j equals 0. We can. But you usually want to start at j equals 1 because you might complicate things when you're writing your Riemann sum, especially as the number of rectangles approaches infinity. So, which one, in your opinion, was easier to write for sigma notation? This one? I mean, I guess it wasn't extremely hard, but we did have to manipulate it a little bit. Or was this one easier? Yeah, the top one. So we're going to be doing sigma notations for all RAM, but I want you guys to recognize we're going to be doing integrals to sigma notation and sigma notations to integrals. I want you guys to realize that we can do sigma notations for any of them. It doesn't have to be RRAM, LRAM, or MRAM. It can be any of them. Now, here's the question for you guys. Can I get the perfect area under this curve?
Yes.
Yes. If I do, okay, so I guess maybe I should rearrange my question better because that's not a very good question. If I made the number of rectangles for LRAM, for this guy right here, approach infinity, and I made the number of rectangles for this guy right here, approach infinity, would I get the same number? Would they converge to the same number? Yes, they would.
Yeah.
So now you're going to see that we're going to start using limit notation. We're going to make n approach infinity. We're going to put the top number and change it to an n. So as a matter of fact, you know what? Let's do it. You know what? Let's go back to this first one here.
Wait, you said add an n?
Yeah, let's do this approach infinity. See if we can. I don't know. We might not be able to.
Oh.
So if I made this approach infinity, the number of rectangles, so my delta x, you know what, maybe I should change the color, right, to burnt orange. So I'm going to say, so everything in burnt orange means n approaching infinity. So my delta x, if n is approaching infinity, would be 2 minus 0 divided by n. Right? And I got to introduce another letter. So n means that I want the number of rectangles to approach infinity, and then I'm going to say k stands for the kth rectangle. Chavez, what are you talking about? Isn't n just the number of rectangles? Why can't you just use n? You're right. But I want to number my rectangles like the kth rectangle, the first rectangle, the second rectangle, the third rectangle, and I'm using the letter k to show for it. And then I'm using the letter n just to mean infinity. So here's what I'm trying to say. You see the sigma notation that I'm writing? In the bottom, I'm going to write k equals 1 for the number of rectangles. And what letter do you think I'm going to put in the top? N. And what do I want n to approach? Infinity. So to the left of this, you're going to write limit as n approaches infinity. So if n approaches infinity, let me see, how would this expression look like? It would look like this, f, and remember, the k stands for the kth rectangle, the first, the second, the third. So all I got to do is put 2/5, and then next to this 2/5, I put the letter k. Close it, times, not 2/5, times 2 over n. And this will always give me, this will give me the exact area under this curve. Now, if you try to do this in your calculator and put 1,000 rectangles, it's probably going to take forever. It actually probably will freeze. I don't know. I haven't tried it. I'm kind of scared because, well, I know how to unfreeze it, so it's okay. Do you guys want to try it? All right, look, let's try it. Case, yep. So look, I'm gonna put 1,000. So this is no longer, yeah. So this is 1000. Oh, you know what? I gotta change that to fifth. It's not to fifth anymore. So this is wrong. This is wrong. See, good thing we did it. If I have 1,000 rectangles, my delta x is not 2 over 5. 2 over n. Good job. All right, let's see.
Wait, but why is it 2 over n again? Is it because the number of rectangles is infinity? Because you're dividing by the number of rectangles?
Yes. But right now I'm using 1,000 because there is no way to write n equals limit as n approaches infinity. So that means I'm going to write this 2 over 5 as 2 over 1,000. So the calculator can actually calculate this. And then I'm going to go 2 over, I don't know if it will be able to do it fast enough if I'm being honest with you guys. Let's see, I'm going to push enter and let's see how long it takes. We might sit here for a while. And that's why my calculator is fast. Look, it's just running and running and running and running and running. If it takes more than another 5 seconds, I'm gonna close it. I'm gonna stop it. 1, 2, 3. Yeah, it's gonna take longer. How do you stop it when it does this, guys? You push enter and then you push on. Oh, right as I was about to push on, it did it. 7.32. What do you think the exact area is? Abdul Karim and Romero here already know the answer, but I think it's 7.33. Look. Okay, I'm going to tell you how to find the exact area because we're going to tell you anyways right now. This right here will give me the exact area. And don't worry, I'm going to show you all the secrets of this. Alpha trace y1. And I wonder how close it is. I wonder how good. I bet you it's 7.3333. Look at that. That's pretty close. All right, I know. Let me show you all the secrets of calculus. So don't worry, we're going to get really good at doing this right now. So if you go to this next page, so let's read this together, guys. So how is sigma notation related to the last lesson? Simple. We aim to add an infinite number of rectangles to find the area under the curve. It could be below the x-axis. It could be above the x-axis. If it's below the x-axis, it is signed area. So it would be negative because you have a negative y value times your delta x. But that's fine. That's fine. And it says in each subinterval, we have a vertical rectangle that reaches the x-axis to the curve at, this is just some coordinate. Some coordinate. And I'm surprised, this is coming from the Demena textbook. Sometimes they write c of k. Sometimes they write x of k. It doesn't matter. It's just your x value for your rectangle, for the case rectangle. It says these rectangles can lie, oh, I already read that. Each of the rectangles forms a product. This is your height. And the delta x is your width. See, and it depends on how many case rectangles you have, which is the area of that respective rectangle. Finally, we take the sum of these products. So this is the sum of all those rectangles. So it says here, this is called a Riemann sum. Sometimes they call it Riemann. Go to dictionary.com and type that name and see how it's actually pronounced. It doesn't matter, I don't think. The existence of a definite integral. All continuous functions are integral. That is, the function f is continuous on an interval. Then its definite integral exists on a to b. Okay, so we're already starting to get into the word integral. So what they're trying to tell us is, if we can draw a function that's continuous and differentiable, we can write an infinite number of rectangles and find the area under that curve. So this means exact area. See, where N stands for the number of rectangles. Infinite, and it's infinite because it says limit as n approaches infinity. Infinite rectangles. The f of ck is your height, and the delta x is your width. And so where ck is chosen arbitrarily in the kth subinterval. And don't worry, we're going to do a whole bunch. So Chavez, what exactly are you trying to say? Okay, here's what we're trying to say. This means exact area. The A is the start, x equals A, and then the B is the stop, x equals B, of what you're trying to find the area of. The f of x is your height, and the d of x is your width. All you're doing when you're finding an infinite number of rectangles, you're literally just finding the definite integral. And you call it definite integral because it's defined. So I'm going to write a to b of f of x dx is called definite integral. You're defining it. There is something called indefinite integral. We're not there yet. How do we feel? Okay. And then they tell you upper limit, lower limit, integral from f of f from a to b. You can read that. Excuse me. It says the value of the definite integral of a function over any particular interval depends on the function and not on the letter we choose to represent its independent variable. So all they're trying to say is it doesn't matter, dx, du, d, whatever you want to call it. If we decide to use t or u instead of x, we simply write the integral as blah, blah, different letters. Doesn't matter. No matter how we represent the integral, it's the same number defined as the limit of Riemann sum. Since it does not matter what letter we use to run from a to b, the variable integration is called a dummy variable. So it doesn't matter what we call it. We're still finding the area, something times something. All right, here we go. This is the important part. We're going to go slow. The interval from -1 to 3 is partitioned into n subintervals of equal length. And they're taking away the fun from us, that 4 over n. Okay, we'll show you how they got the 4. Let m of k denote the midpoint of the k subinterval. Okay, this m of k is just some x value on your k rectangle. That's all it is. And what are they using? MRAM. Doesn't matter. Express the limit. So they give me, express the limit of n approaches infinity, blah, 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 as an integral. So they want me to use this. Integral a to b of f of x dx. Remember, guys, this dx is like that delta x. Cool or not cool? All right, now they shouldn't have given us that delta x because it should have been cool for us to do. So delta x, what did I tell you the delta x was? The change in x over how many rectangles we use, right? Okay, well, where do I start? At what x value do I start? What x value do I stop? 3. Just like in physics, it's always final minus initial, so I'm doing the same thing here. 3 minus a -1 divided by n. So I'm kind of bummed that they gave us that 4 over n. That's my delta x. Yay or nay? All right. Remember that I told you that m of k is just some x value? Okay, well, there's my m of k, and we just said that was just some what? Some x value. So I can already figure out what this function is and how this integral is going to look. So, all right, integral. What's my lower limit? -1. What's my upper limit? 3. Are we cool with those limits? And then I open up a function or a parenthesis. And what am I going to type? 3. And then what did I tell you m of k was? It was just some what? Some x value. So I'm going to put what letter? X, yeah. Put a square on it because it says m of k squared minus what? 2x plus 5. Close it. And then what do I put instead of 4 over n? I'm going to put what?
Delta X.
Delta x, but instead of delta x, I'm doing an integrand,
DX.
dx. The difference between dx and delta x, guys, they kind of mean the same thing. But remember, like we did when we were doing derivatives, delta x is like it's a significant gap, and dx we're literally approaching zero, like because it's so small. So you know what? Let's add this here. Go to right here, this formula. Sometimes it depends on the professor. I've seen it in MIT and different universities. Sometimes they don't use n. Sometimes they will say, okay, they'll say this. They both mean the same thing. Limit as delta x approaches 0, or limit as n approaches infinity, in case you go to MIT or one of those and they decide to do that. Chav, why is it the same? I don't get it. If the number of rectangle is approaching infinity, that means my delta x is approaching 0. Think about it. We're putting more and more rectangles. The more and more rectangles we put in here, doesn't the delta x get smaller and smaller? Yeah. The more rectangles you put, the smaller and smaller the delta x approaches. Don't be a robot. So, Chav, I went to MIT. They didn't show it like this. They used delta x approaches 0. It's the same thing. Limit of delta x approaches 0 means the number of rectangles approaches infinity. Does that make sense? Okay, good. All right, here we go with the next question. Okay, before I start, maybe I should have started with example 4 first. No, I'm gonna start with example 3, and then example 4 I'll show more detailed. Yes. Okay, before I start example 3, I'm gonna show you the steps, but I would like for you to not be a robot. Can you be a robot? Yes. You just follow. I need a delta x and I need an x of k to figure out where I'm at all times, and I'm just going to plug it in. Yes, you can do that. But try really hard not to be a robot. All right. Write a limit using sigma notation. So now they want me to write the whole with the sigma notation. So I need delta x first. Delta x equals. How do I find it? Yeah, b minus a, 7 minus 4, and I'm dividing. Remember, I'm using an infinite number of rectangles. I don't have 4, I don't have 5, so I'm not going to divide by a number. I'm going to divide by what letter? Instead of x, I want n rectangles. N. Perfect. So what's 7 minus 4? 3. So 3 over n. Cool or not cool? All right, our first rectangle, we're using our RAM. We're using the rightmost RAM. So my first, I'm going to write x of k for, because we decided that. Remember when we did question 1, this top one, and then question 2, and we said which one looks like it's easier to come up with a formula for, and you guys voted for this one because we didn't want to mess with this j minus 1 stuff. Okay, so we're using our RAM. All right, we decided that. So I'm getting the x value. So this x of k means my x value at the kth rectangle. Well, my first x value, the very first one, where do I start again? 4, but I'm not using LRAM. So I'm gonna add, look, this is my delta x. So I'm gonna add my delta x. It's always gonna be this, 4 plus the kth rectangle times delta x. There's my formula, but I don't want you to be a robot. Think about why. So let's see. X of k is going to be 4 plus 3 over n. Usually you want to put the k in the end like this. So 3k over n. Chav, I don't understand why. Okay, I'm going to make it simple. Let's pretend that we just had 3 rectangles. So don't write this down, just pretend. Don't write this down, just pretend. So if I just had 3 rectangles, do you agree that my delta x will be 1? Okay, so if I want the x value of my first rectangle, remember I'm using RRAM. I start at, so look what you're saying, 4 plus 1, right? Because we're saying that n is 3. Don't write this down, just listen. So k equals 1, my first rectangle, and look, 3 over 3 is 1. So my first x value is 5. That makes sense, because delta x is 1. My second rectangle, that next value should be 6. Well look, if my second rectangle, if k is 2, this is 3 times 2 divided by 3, so that's going to be 2. 4 plus 2 is 6. See how it gives me that second rectangle? The third rectangle, it better be 7, the x coordinate. Well, look, if this is my third rectangle, remember, k means the rectangle number. 4 plus 3, 4, 5, 6, 7. That x value is 7. Does that make sense, guys? So we're not being robots. Okay, I'm going to erase this because it's not part of that situation. So let me go ahead and erase that yellow stuff. Okay, here we go. I got everything I need. 3k over n. I'm going to write it. I'm going to write limit as n approaches infinity. You can also say delta x approaches 0 of my summation. And where do I start at? Oh yeah. But my k value, the lower sum, is going to be a 1, and I'm going to go all the way to n. And then the height of each one of these rectangles is going to be 4 over, and you're right, I started my x value, so here you're always going to type in your xk. It says x, it's always going to be this guy. So it's going to be 4 plus 3k over n, and then plus 4, close it. That's my height of each rectangle, of the kth rectangle, and I'm going to multiply it by your delta x, which is 3 over n, and that's the first one. How do we feel? I know it's hard, guys. That's why with example 4, that's the one that I did an x squared there on purpose. I wanted to do a hard one first and then go to easy one. And okay, well, check this out. Let's go to this one. Write a limit using summations that would equal this. Okay, let's pretend for now, I'm going to do it in black. Let's see, that's 5. So let's pretend we're just using 5 rectangles. So then that would be simple. Everyone knows how x squared looks like. So here is in black. Everything in black is just going to be that. I'm going to say here is 6. I'm going to say here is 1, 2, 3, 4, 5. Okay. And I said we're using RRAM, right? So 1, 2. This is just, I'm just making this up, guys. 3, 4, 5. 1, 2, 3, 4, 5. Then I would go, let's see, what would I do? I would say that my delta x is just 6 minus 1 divided by 5, which is just 1. I feel warm now. I feel really warm. We're cooking. All right. Then I'm going to say, I'm not going to use the limit notation because we have 5 rectangles. So I'm going to say k equals 1 to 5. And then in parentheses, where do I start? At 2, right? So I'm going to write 1 plus k, close it, squared, times 1. And that would give me the area under the curve with 5 rectangles. Do you guys agree? All right. Are we doing it with 5 rectangles though? Like, does the question want it with 5 rectangles? No, it wants it with an infinite amount of rectangles. So here we go. Here's how we do it. Limit as n approaches infinity, sigma notation, k equals 1 to what value? N, parenthesis. My kth rectangle is going to have what x value? 1 plus, well, I guess I should have done this first. Delta x, 6 minus 1 divided by the number of rectangles, so 5 over n. We're using RRAM, so it will be 1 plus 5 over n. But remember, I'm doing this like right now, this is only going to give me the first rectangle. What if I want the second rectangle? It's not plus 5 over n, it's plus 10 over n. So what letter do I put next to it? K, and that will work. Do you see? Second rectangle, 10 over n. Third rectangle, 15 over n. Fourth rectangle, does that make sense? Close it. What do I put on the outside? Squared. And then I'm going to multiply this by your delta x, which happens to be 5 over n. So there it is. So is this making sense now? Now notice, so you can always do this. If you want to, x of k is always going to be your a, which is where you start, plus your delta xk. Oh, delta xk. No worry, I just erased that sign, whatever. It's always that. It's always, always, always. But I don't want you to be a robot. Does everyone know where this is coming from?
Yeah.
Okay, Abdul Kareem, you know where that's coming from?
Yes.
Marchan, Flores, are you guys there?
I'm here.
Does this
But
kind of
yeah.
make sense?
Yeah, we're
Yeah,
good.
it makes sense.
Okay, okay. I'm
Yeah.
happy, guys. I'm happy. Let's keep going. Let's keep going. So let's see. I want, remember, we're just practicing with limit notation, with sigma notation. So I want infinite amount of rectangles. So I'm going to write limit as n approaches infinity, where k starts at 1 all the way to n. And then on the side, I'm going to go, my delta x is, and I write 2 minus 1 over n. You don't have to do 2 minus 1 if you already see it, that it's just the difference of x over n. So 1 over n. And I know that my x of k, that just means the x value for the kth rectangle. We're using RRAM. Is going to be 1 plus k over n. K times delta x. So I come back and then I know there's a square root there. So we put a square root and then we just put the x of k. Wherever there's an x, we put the x of k. 1 plus, I like to put parentheses here just in case. Close it. And then I'm going to multiply that sucker by 1 over n. Make sure the 1 over n is outside the square root. How are we feeling? Perfect. Chav, what about this one? Oh, okay, actually this one's still the same. It's the next one that's going backwards. Chav, what about this one? Same thing. We do the same thing. Delta x equals 6 minus 4 divided by the number of rectangles. So 2 over n. And then the kth rectangle, the x value, where am I going to start at? 4. It's always a plus. And then k times delta x. So 2k over n. If you want to put the k in the front, that's fine. But usually we put variables in the back. And so here we go, guys. Limit as n approaches infinity. Sigma notation. From k equals 1. Child, why do you keep using k? We can use any letter, but k is the one that that is universally accepted, that it's common for every textbook has the letter k, pretty much. All the way to n. ln, parenthesis, and then the k value is what you're going to put in there. 4 plus 2k over n, close it, and then I'm going to multiply it by 2 over n. Okay, guys, don't freak out. Sometimes they will try and trick you, and they will show it like this. Limit as n approaches infinity. And then they'll say this, k equals 1 to n, and then they'll do this. Are you going to freak out? No. It's still the same thing. This 2 over n is still, that's just the delta x. And then this is your height. It's still the same thing. Now your integral, you always write your dx in the back. So for the integral, you know what, this is a good side note. For the integral, you will never see this. Because this means integrate 1. So that dx is like the end. And then times dx. This is a no-no. It will always be like this. The dx means the end of your integrand. Does that make sense, guys? Okay. All right. Here we go. Relax. This one has a lower limit of 7, an upper limit of 5. It's still the same. You're just going backwards. If you wanted to switch the limits and put a negative on the outside, you could, but we haven't talked about integral properties yet, so let's not go there. You could just go delta x the same as always. 5 minus 7 divided by n, and you get negative 2 over n. Just do that. And then, remember, that 7 is the start. So x of k equals, I start at 7. And if you want to put plus, that's fine, because we're going to subtract anyways. 7 plus, what do I put? Yep. And there it is. If you want to get rid of the plus and put a minus in the front, as long as you don't put the negative there, because minus and negative is positive, you can do that too. You can do x of k equals 7 minus 2k over n. It doesn't matter, whatever you feel most comfortable with. And then we go limit as n approaches infinity, summation, k equals 1 to n, parenthesis, and then I write 3, open parenthesis. Where do I start? Well, I guess, yeah, I usually say that when I don't write x of k. Just type in your x of k. Hopefully you get so good that you don't need to write that. You can just go right into it. But it doesn't matter, guys. Whatever you guys want. Close it, dx. By the way, you don't necessarily, on the integral, you don't necessarily have to put a parentheses because it's understood that the dx means end. So they could have done it like this, 7 to 5, 3x plus 1 dx. And then sometimes people are like, that means 1 times dx. No, the dx means you're ending, so this is still your function. So you don't have to put parentheses. Some books put them, some books don't. It just depends who the author is. Yes. Oh, it is not a dx. It is not a dx. Sorry, I was, yeah, it is not a dx. It is not. Do not write dx, so that's a sigma notation. Negative 2k over n. Yeah, I make mistakes all the time. That's a big one. That's a huge one. Another one. Yeah, it's not an x value, it's a delta x, so it's just negative 2 divided by n, number of rectangles. Mistakes after mistakes. Okay, we got them though. Cool or not cool? Okay, let's do this one here. So delta x equals 3 minus 1 over n, so 2 over n. And x of k equals, where do I start? 1 plus 2k over n. You can see how it can be very robotic because it's the same thing, but we're not robots, right? Okay, like we know what we're doing, right? Limit as n approaches infinity, summation from the first rectangle to the infinite rectangle and to the, put the n, and then parenthesis 4, open parenthesis again, put your x of k, 1 plus 2k over n, close it, put a square on it, plus 2, close that, open parenthesis, put your delta x, which is 2 over n. And yeah, they're all pretty much the same. We're using RRAM. Could we use LRAM? Yes, we can. But there it is. So now you know that this means exact area. Cool or not cool? Cool.
If it's LRAM, we would use.
Oh, if it's LRAM, it's going to complicate things. But yeah, remember we have when it's LRAM, we have this extra. So if we're going to start at k equals 1, it could be done, but it would be a little tougher. How do we feel, guys? Okay, so let me stop sharing this. And hold on, I guess I'm gonna have to stop recording.